information that Dr. Luke will be sharing with us. His research interests reside primarily on observations of physical oceanography and span the wide range of spatial and temporal scales of the ocean. So he has worked on large-scale circulations to small internal waves, turbulences. The projects he has involved in focuses on interactions between various phenomena of different scales. So on a large ocean scale as well as on small scales like eddies. Many of Luke's projects revolve around finding innovative ways to study the ocean, pushing the boundaries of what we have observed primarily through seagoing oceanography. And he has developed an instrument, a special glider that could collect and record data in the ocean. So I invite Dr. Luke to address us. Thank you.
Sorry. Thank you very much for inviting me. It's really a pleasure to be here and share this experience with you. So the main objective of this goal, of this talk, is to share my passion about the ocean and give you a flavor of how we observe the ocean, how we interact with the ocean, and as a scientist, as a physical oceanographer, what kind of tools I use to look at the ocean. So let's see if it works. Yeah, perfect, thank you. Great. So a quick outline of the talk. I'll be talking a little bit about our experience and how we observe the ocean, so going back in history and how the way that we interact with the ocean, the way we observe the ocean has been changing. And really that goes into presenting you a quick overview of what kind of tools we now have to understand this vast ocean around us. And I'll give you a couple of examples of process studies, the kind of instrumentations, the kind of observing system that we design to be able to understand the process that's all happening in the ocean. As a scientist, you're always observing, so by definition, by nature, you're sort of a little bit removed, but of course, observing the ocean, as a scientist, your motivation is really personal. So I want to start here by just talking quickly, just giving you a few slides about who I am and who I work with. So I grew up in Canada, on the East Coast in Quebec, so the northeast corner of North America. I went to college in Montreal in Canada, so I grew up speaking French. And after college, I wanted to go and travel the world, try see something different, but I had no money. So I went to school in the United States at San Diego, at the opposite corner of the North America in the Southwest, at Scripps in San Diego. So that's where I did my PhD. And I worked in a couple of other places in the States, but have been in Seattle for the last many years now. I work in a very wonderful group. My colleague Craig Lee and I are leading this group that really has a partnership between science and engineering. The science really drives the kind of questions we go after, and the discoveries that we make really motivate the science. And on a really small scale, that's what's happening on our group, but if you can think of oceanography, of ocean science, really as this marriage between science and technology. Both of them work hand in hand, and it's really that's the theme of the talk for oceanography in general, but particularly for what I do. And I think that's part of why I love studying the ocean, really being able to interact with the ocean, both with my instruments and that feeling of discovery that you get from doing science in this really wonderful part. And just quickly, the map here shows a map of sea surface temperature, sea surface salinity from space now that kind of gives you this big picture of where the world is. And what you can really see the differences between the two basins. Between the basins, the North Atlantic is much more salty. Pacific Ocean in general is a little bit fresher, especially near at high latitude and also near the equator where you have a lot of rain. And one thing that really is striking in this figure is if you look at the Indian Ocean, just south of India, you have the Bay of Bengal that's really, really fresh because of all the big rivers that come, so lots of water that is much less salty than if you go on the other side of the Indian Peninsula, where you have the Arabian Sea that is really salty on a global scale. So that really strong contrast really comes here at a crossroad near Sri Lanka and near the Maldives, and that's part of why I'm really, really interested in this part of the world and why this is a fantastic crossroad for all the kind of processes that we're interested in. There are big stars where, like, our group has been working in the last many years, so we work all over in the world looking at a process because the physics of the ocean really is kind of across boundaries, across the different places, across the different regions. So again, that speaks to this, the words that we heard this morning and that we're going to keep hearing during these 2 days about this cross-disciplinary and cross-border. And that's really the kind of things that we do. So very quickly, why do we observe the ocean? So a big part of it is always that feeling of discovery. So we want to understand this wonderful environment that we're all right next to. And oceanography is really that feeling of discovery, trying to be at the ocean, trying to understand all of these processes. And again, science, the currents, the ocean itself doesn't know any boundaries, and the science, by its nature, this is a really wonderful quote from Louis Pasteur from a few hundred years ago, but it's really that idea that the science is really where all those partnerships and that community is built. When we observe the ocean, when we collect measurements, what are the big motivations for doing this? There is that discovery, and that's kind of where I sit, the basic research, trying to understand these really interesting and important processes. You come up with questions, and you come up with ways to try to increase that knowledge that you have of the ocean. And in turns, by understanding that processes, by having a better idea of the physics of the ocean and the biogeochemistry of the ocean, then you can improve numerical models, you can extend that knowledge to different regions, to different processes, and so on. So there's that basic research side. But there's also, as we heard this morning, the policy side is very important. We live in this world that is all connected to the environment that we live in. So in terms of fisheries, climate mitigations, sea level rise, and having these policies that are informed by data and collecting the data that really allow you to make sensible policies. And similarly, operationally, the ocean and the atmosphere and the world that we live in really matters into our activities. So being able to do better weather forecasting, better tactical characterizations, meaning that if you want to understand the environment, there's an oil spill, you need to figure out where the oil is going. There's some specific observations that you will need for this, specific tools, but it all kind of goes back to these efforts of basic research that you did. So these three pillars in many ways are connected, but they each have their own needs and own reasons. So I'm going to walk very quickly here through a quick history of what ocean observations have been and what they are. And really the goal of these, of the next few slides is to talk about this, the special role of observations. Why do we actually need to go out there in the ocean and collect measurements? And it all comes back to that symbiosis between basic research and technology development. Discovery drives the need for more tools, and the tools really allow you to do more discovery. As humans, for as long as we lived in this planet, the ocean has always been a big part of our environment and where we are. Especially here in the Maldives, the ocean is everywhere. And from very early on in the history of humankind, we've started to try to understand the ocean, trying to live with the ocean. A lot of it was motivated by trades and for fishing, for resources. But very early on, in Polynesia, for example, they started understanding how the swells was refracted around the islands, how the stars could help you navigate. So there's very early observations of how the ocean works and how the atmosphere interacts with the ocean. Here in this part of the world, about 2,000 years ago, already traders were going from the east coast of Africa to Arabia using the monsoon winds. So there's that connection that really started happening. But through all of this history, until very recently in many ways, the ocean was we tried to understand the ocean in order to navigate or to use the ocean for resources. Following, this is kind of like, again, the big picture, following the kind of around the late 1400s, 1500s, where the explorations, both on the Asian side, China explored pretty much the entire Pacific Ocean in India, and at the same time, you had British expeditions and Spanish expeditions going and mapping about half of the surface of the world in that really interesting part of history. But following this, people started also using these expeditions to collect data and to try to understand the ocean. The Beagle and Charles Darwin expedition is one of those most famous, and that's really kind of the beginning of the science as we know it today, trying to do observations, trying to understand it. And that was followed by, trying to understand the wind and the wave current patterns using all these ship logs. So people starting to look at all that information that was collected and trying to understand, if you put a message in a bottle, where will it end up? What are your... so it was kind of trying to get this mechanical understanding of the ocean. The first scientific expedition in many ways was this Challenger expedition that kind of went all around the world, although I note here that it completely ignored the Indian Ocean. But this is an expedition from England that came in, and that's really normally viewed as sort of the first true oceanographic expedition. A lot of it was enabled by this building, this feeling of discovery and exploration that had been happening in the previous couple of 100 years, and also some very nice scientific innovation. The reversing thermometer, for example, that was invented by some of the Scandinavian scientists at the time, that allowed to measure the temperature at depth. So being able to collect really interesting data in depth sounding and so on. So these expeditions were kind of the first time that scientists were out at sea trying to understand the ocean itself. I'm going to take a really big leap here, and in a sense, the first modern physical oceanography, there's a lot of development that happened in the technology between these times. But one of the first time that a bunch of scientists really got together, starting asking questions about what kind of science they wanted to do, and they really planned this dynamical experiment based on modeling and some analytical results that they were getting. So there was this experiment called the MODE experiment in the North Atlantic. And I recommend this. Part of why this is also emphasized is that there is this really fantastic documentary of really early physical oceanography that is on YouTube, really. So it's kind of interesting to see what the science and what kind of scientists what kind of questions the scientists in that time were asking. But that was really kind of a way that kind of set the stage for how we do observational oceanography right now. And that kind of progressed through the 80s, through the next few hundred years, with this big kind of coordinated effort called WOS that was really going with big ship and measuring temperature, salinity along all these different lines, so crisscrossing the globe. And from that, a picture of the ocean emerged that was both, kind of this large-scale circulation where you have the western boundary currents and general gyre circulations, equatorial circulation, sort of a quasi-steady circulation. But on top of it, there are all these eddies and swirls and all of that dynamics and that physics that came. So it was kind of this idea that you can do these big ship sections, get a snapshot of what the ocean is, but also an emerging realization that fundamentally the ocean is constantly changing. And that really set the stage for the next few really big improvement in science in oceanography and observing system. I'll just, this is kind of a little a break here to just really make the point that oceanography in general, and that's true for many other sciences, are not really big market. You can't really drive the technology, you can't really drive a lot of these really fundamental electronics development but these science in general is also very good at taking advantage of all the other developments that are happening for all sorts of purposes and adapting it to our needs. So this is just kind of going on one side. On the left-hand side, you have kind of the big technological advances that happened in the last 50 or 60 years. For example, in the 60s, you had a lot of these circuit boards that were, these computers were being invented. And in the 70s, you started having these tape storage and so on. And at each step, the science community was able to adapt this. And by the time you had, for example, in the 70s, some tape storage ways to record the data that was really fundamental for the computing industry, you were able to then put current meters and deploy them in the ocean and record that data for longer periods of time. So for each of these technological advances, and if you look at more recently, the fact that we have cell phones that are really low power, that have really great chips, really allow us in many ways to be able to make the type of observations that I'm going to talk about in a minute, these autonomous gliders, these cable observatories. And more recently, we have these Apple Watches and these other things that can sense blood pressure and have like really fantastic little sensors. And that, there's no way that I could have developed this so that we would have, the funding agency would have the energy to, and the money to, the resources to do this, but we can adapt this to get these multi-sensors on our platform, and that allow us to actually do sampling across disciplines to sample different scales to different time scale and so on. And just a nod to the the AI, artificial intelligence and network really also allow us to use all of that data and kind of make sense of it. So I'm going to give just a couple of more modern examples of observing systems that are really key to the way that we understand the ocean now. So starting in 2000 or so, people are starting developing deploying these floats. So they are like they're autonomous floats, these things that are about like half a meter long or so, and you put them in the ocean, and then they just kind of once every 10 days, they do a profile measuring temperature and salinity, then they drift for 10 days, and then they come back and then do another profile. And there are 3,000 of these floats that are deployed in the ocean. They last for about 4 or 5 years. And through a global effort of many different countries, this is a big international program that many people contributed long-term. And now we have this sustained observations that, we get 9,000 CTD profiles per month over the entire globe. So that's kind of a distributed network, and I'm going to show you some example later of the kind of data that you get from this. But this is kind of this great way to map what the ocean looks like at any given time on kind of a basin scale, on a much larger scale. Similarly, there's this other program, the Global Drifter program, that then looks now just at the surface and how the ocean moves. So we can measure the temperature and salinity with these floats. But these global drifters, again, this is an international partnership. Many different countries contribute and put those drifters there, and they all kind of are pushed along by the ocean current. This is an example of a study that we did a few years ago around Sri Lanka, that you deploy these drifters and they kind of go around Sri Lanka depending on the different monsoon currents. And zooming in, and this is just looking at earlier this week, where some of these drifters are around Maldives, and if you kind of take the one that is just east of Mali, for example, it kind of like you can click on it and it tells you, well, this came over the last the last month or two. It was deployed north of India, like somewhere in the Arabian Sea, and has been kind of slowly going along the side of the coast of India, and now it's kind of heading for the southeast Indian Ocean. So all of that data kind of gives you that example of what the broad pattern of the ocean is doing. My tool of choice, the thing that I really use mostly is kind of trying to, within that big picture that the glider data, the float data and the drifter data gives us, is using these small autonomous buoyancy-driven gliders. So these are things that are about the size of one person, and they're little robots. You can think of them as little airplane robots that are very, very slowly. They just kind of dive down in the water column, and then they come back up 6 hours later. So they go from the surface to 1,000 meter. Their mass is fixed, but I can change the volume by pumping oil in and out of a bladder. So you can effectively change its buoyancy, so it becomes heavier than the water around it at the surface, so it sinks. And by the time it reaches the depth that you're interested in, you can then you can increase the volume, so you become more buoyant than the water around it, and you can rise. Because you can change the pitch and the roll by moving masses inside the glider, you can just direct the glider to a direction. The glider can itself find its directions in the directions it wants to go. And so very slowly, about 20 kilometers per day, you can do these sampling, and along the way you sample any properties that you're interested in. So kind of 20 kilometers per day, by doing this like slow yo-yo up and down, you can measure properties of the ocean, of the water column. So there are different kinds of glider. This is an example of one of them being deployed from a ship here. And since about 2000, since the time that actually I was a graduate student, different types of these gliders have been developed and now are kind of used operationally all around the world. And mostly it's looking at these processes, at these targeted regions where we're interested in having higher resolution data. So as I mentioned, they're slow, but they're persistent. So these gliders can be deployed for many, many months and be completely kind of doing their missions autonomously for extended periods of time. So at the surface, it just has this tiny little antenna that allows the glider to share data and to communicate. So you can see in the middle, barely you can see this little red antenna sticking out. So the glider is kind of, again, this person size with a little antenna now sticking out of the water column. And by the time it wants to dive, it made itself a little bit heavier than the water around it, and it kind of slowly glides down in the water column. So this is an example of a more recent example of one of those gliders that we deployed in the middle of the Arabian Sea in about 5 years ago, or almost 10 years ago, actually, in the northern Arabian Sea. And our plan was to go to the Seychelles with it. So very slowly, it kind of makes, again, 20 kilometers per day. So it takes many, many weeks, if not months, to go all the way from the northern Arabian Sea. And because of currents, the glider, again, doesn't fight currents really well. Instead of going to the Seychelles, we decided to take a right turn and hope for recovery somewhere. And eventually, this glider was recovered here in the Maldives. This was, I think, the first or second time that I came to the Maldives by working with the Maldives Meteorological Service and a nonprofit foundation, the Maldives Whale Shark Research Program. They helped me, and I went to collect this glider and that data. So this is the kind of data that this glider will tell you. So it's a little directed, and so these pictures, I'm just going to walk you very quickly through this. So as a function of depth and space, so this is from 15 north, the northern Arabian Sea, and as a function of space all the way to the equator, the glider kind of travels slowly up and down, measuring temperature on top and salinity at the bottom. So the colors are kind of an idea of what these ocean properties are. So that's kind of a slice across the ocean. So you see kind of warmer water at the top, in this case saltier water, especially in the northern Arabian Sea, and less salty water at depth near the equator and right at the surface near the equator. So this is kind of how I visualize all the data that does it. And this is kind of the things that get oceanographers really excited. And that's why we really love looking at this, because by just the same way that if you look at clouds moving in the sky, you can tell what the wind is doing and where maybe they come from. So this tells me I can look at these properties and see that high salinity water right at the surface in the northern Arabian Sea. I can trace it back in my mind, and through the knowledge that we've had over these many years and all that data set, we can trace it back. So that's water that was formed and got its property in the Gulf of Oman. And a little bit deeper, you have water that got its properties in the Persian Sea. And by kind of piecing this, all these properties together, and here I'm showing only 2 of the variables that we measure, but we really get this picture of how the ocean looks like and where each of these water parcels come from and where they'll go. So this is the kind of data that gets us, again, excited, and we see all sorts of scale. So that's another point that I want to make here, that we have this broader picture, warm at the top, colder at the bottom, saltier in the north. But if you start looking in details, the more you're looking at the ocean, the more details, the more processes you'll start seeing. And that's really a fascinating aspect. And that's kind of emphasized by this visualization. This is from a numerical model that NASA is running, and the little lines, the little wiggles show you ocean currents at the surface. And you see, in addition to kind of the larger scale, like here, this is kind of the end of the southwest monsoon. The northeast monsoon just started in this case. You can see like strong currents going around the tip of India. So all these swirls, you see the large scale, you see these eddies, and you see all these scales overlapping temporally and spatially. So the ocean has this really complex ocean currents, and we know this a little bit from being at sea. But the observing system that we're developing over the years really have allowed us to kind of get this really wonderful picture of how everything of all of this is overlapped. And I just want to show a quick example of one of these process studies. The movie that we just watched kind of ended in the Western Pacific. So last year, for example, we had this experiment in the Western Pacific to try to really look at one of these big eddies, one of these like little swirl that was going around in the movie. So here I'm going to show you. So there's a cruise track so the ship, a ship left Palau, went in the swirl in the eddy that we're interested in, and ended up in Guam. So again, so this is Taiwan. PRC is over here. Japan is going to be up there, and the Philippines are over here. So this is Western Pacific. And I'm going to show you, the next slide will be a little movie, and you'll see the ship coming and deploying all of these instruments, these autonomous instruments that we've been talking about. So there's going to be a bunch of gliders, like 3 different kinds of gliders that I mentioned earlier, including 2 or 3 of my gliders, and then a bunch of surface drifters, floats, and these other tools that I just mentioned. So this is kind of going quick. So the ship goes, deploys all the gliders, and you can see the gliders are things that I can drive. So I can control where they are. And in contrast, the drifters, the surface drifters and the floats, so these are little floats, the surface drifters are the purple, they're kind of advected with the ocean. So by using all of these different tools, I'm starting painting this picture of how the eddy really kind of moves things around at different depth, and I can control the gliders. And by the time I'm done measuring my eddy, I can drive the glider back to Saipan in this case, and we spent a little bit of time taking some measurements near Saipan, and then we actually went and recovered in September all the gliders from the Northern Marianas from Saipan. So that kind of is using all of these different tools to get different perspectives and different views of the process, in this case a big eddy. But the process we're interested in, we're trying to figure out both, in that view of, following the ocean, following the circulation, all of these floats and the drifters that are happening, and the things like the autonomous gliders that I can drive, and kind of a more fixed frame of reference, I can measure the ocean. So you get these different tools that allow you to get different views of what the ocean is. And all of this is in the context of the information we get from satellite remote sensing. So in the last 20 or 30 years, we really got some really great advance. So this is, again, focusing on the Indian Ocean, where we see sea surface salinity, that huge contrast. So I separated here between the northeast monsoon and the southwest monsoon season. what the sea surface salinity looks at the top, what the sea surface temperature looks like, and then we also can measure surface currents with different satellites. And that kind of gives you a global map with kind of a fairly good time resolution, but it really gives you a great idea of what the long-term averages, the trends, and the context of your data. If we zoom in around the Maldives, I'm just going to spend a few more slides talking a little bit more about the Maldives here. But it's no surprise here that the monsoon really drives the circulation quite a bit. So there's one panel here for each month. And if you go kind of in December, January, February, you have the winds coming from the northeast that really brings a lot of that cold, fresher water that is in the Bay of Bengal towards the Arabian Sea, all the way past the Maldives. So it kind of like hits the Maldives, the low salinity water starts pooling there and forms these really shallow mixed layer. By the time April, May comes, this becomes really warm. All that solar radiation is trapped near the surface, so you get these really strong warming. So that's the process that I'm really interested in. And then by the time you get June arrives, you get this atmospheric convection, the onset of the southwest monsoon, lots of rain in the Indian subcontinent, and these really strong currents that completely reverse and now bring that salt water all the way back to towards the Bay of Bengal. So that's what we see from the surface again, but the big question again is how do we observe this to try to figure out the vertical structure of these? So starting to put all these pieces together really quickly, here I put a little dots. This is an example of 2 years of data. The blue lines are the glider measurements that I've been conducting south of Sri Lanka. So you can see that we deploy gliders and they kind of go back and forth between true north and more or less the coast of Sri Lanka. And that really allows us to capture these currents and the properties of the water column right in that really important crossroad. And it is in the context of all these Argo profiles, these float profiles I was telling you about. So I put a little dots for those 2 years during each of the 3 months, December, January, February, May, April, March, April, May. And then this is more the southwest monsoon time, and then September, October, November. It kind of gives you an idea of the different scales that we can resolve using, again, these different tools. And that's the same kind of observing system that is being used. This is one that is really well established. Similarly, glider tracks and Argo floats off the coast of California from one of my colleagues, Dan Rudnick. So that kind of observing system is really the type of things that we're all trying to do. And again, it's using that multi-platform to really get to all the different scales we're interested in. So stepping out a little bit, this is the kind of glider observations that our group has been doing in a really strong partnership here with many people. So we've been working in Sri Lanka for many years, for the last 10, 12 years, trying to measure these flow from across the 2 basins. We also participate in the big experiment looking at kind of the variability and the salinity and the evaporations in the Arabian Sea. So that was using a lot of autonomous processes during kind of 2016, 2018. And in many ways, some of these gliders had to come here to the Maldives, and that really motivated me for starting to talk to people about the really interesting ocean process happening around here. And all of this kind of leads to our current goal of trying to maintain these occupations and maintain, trying to understand the ocean properties that are coming south of Sri Lanka, but also kind of linking them with the type of processes happening much closer to the Maldives. And then we're really hoping to kind of start measuring and partnering here with MNU and with the researchers around here to kind of get all of that observing system in place. So just zooming in very quickly to Sri Lanka. So we've been working there for a long time, and as I mentioned, none of that work is possible without these really strong partnership. The data we collect has to be relevant to the questions that I'm interested in and that my my sponsors are interested in, but it's also data that is relevant for the people who live here, for our colleagues in Sri Lanka, again, to inform policy, to inform operations, and to inform their thrust for knowledge. And so we work again with NARA and with Ocean University in Sri Lanka, And this is the kind, again, just like the same example, like very similar example that I show you, looking at salinity and temperature. And in this case, Sri Lanka here is kind of showed in gray. There's a lot of shipping, so I'm trying to avoid the little gap between Sri Lanka and the end of the shipping lane. So I'm missing kind of 30 or 40 kilometers. But this is sort of a 400-kilometer section, again, as function of depth and latitude. So this is 400 kilometers. And looking at the salinity properties and the temperature properties. And again, it's really amazing to see how rich, how much structure there is at all different scales. So you can really see that fresh water. This is during the December, so the northeast monsoon, fresh water coming around, and saltier water that originates from the Arabian Sea, kind of, again, flowing sort of under the surface. So what you see at the surface is really not the same thing as what you see inside the water column. And that has really big implication for the kind of processes that we're interested in. So there are really strong gradients. And it takes about 3 weeks for a glider to do this 400-kilometer sections. By the time I come back next time, the ocean has changed quite a bit. So all that fresh water that I saw at the surface is gone. So there's a lot of variability, and the ocean is really changing, and that's really something that is fascinating. And I'm just going to end with a couple of slides here about I talked a lot about the physics, but of course, the ocean is a much more complex system than this. There's physical oceanography, there's biology, there's plankton, primary productivity, there's geochemistry that happens. And you can't understand biology necessarily without understanding physics. And the physics also depends in many ways on biology, on ocean colors. So there are a lot of different overlaps. And again, all of this happens on many different types of scales, and they are systems that are linked. You can't look at only one part without looking at a bigger picture. So this is an example of just an image, a false color image of chlorophyll at the surface, and it would be prettier in color, but you already see a bunch of structure at all sorts of scale. There's like these really large scale, these smaller scale, and this is for a different experiment that happened in the North Atlantic at Bloom, where we measured chlorophyll as function of depth and time. So this is about a 2-month period. This is from a glider and looking at nutrients. And the only point I want to make here is how complex these spring blooms and these interactions between the physics, and that's really, you can see chlorophyll patches coming in and the nutrients being depleted with a lot of carbon export. And all of this lives on top of these fronts, this mesoscale, submesoscale structure that is really important to capture. So that's kind of the main point. If you kind of think of the ocean as being a continuum of different spatial scales on this axis, and different time scales, you kind of have, like at the top corner here, you have the decadal, like El Nino, and these processes that happen on really long time scale and really large time scale. And you have these eddies and the main currents that we're talking about, all the way from surface waves and turbulence. So the ocean really is kind of this sea of scales. And what's really interesting here too is that all these processes overlap. It's kind of nice because we have all sorts of tools also that overlaps in space and time the same way. So we can measure, we can put a mooring in the water and measure really precisely at one point. We can have a glider that is slow but covers some ground. We can have these drifters that kind of are advected at the surface. So each of these different tools we have, the same way that the processes overlap, the tools overlap, and each one of them is not necessarily the best solution. And I would say that this is actually true for science in general and for community and for what I do. Like, I can't do what I do alone. Each country cannot observe the ocean, ignoring the ocean in other countries. The ocean currents don't know any boundaries. We don't have, and as scientists, we're bound to try to work together and to follow the systems and follow the guidance. So the collaboration and international partnership is really a cornerstone. And again, one of the big message that I hope I was able to communicate here is the fact that discovery really drives that need for better technology, and then we can look around at what is available and be creative. And by the time we have better technology and we have these tools, that opens the door to more discovery. So it's really that interplay between science and technology, the interplay between the kind of questions that I'm interested in and what I'm hearing when I talk to all of you. And that really is what drives this pursuit of knowledge and ocean physics. So thank you.
Thank you very much. That was very interesting and fascinating, I think, for many of us. Now I invite the audience to ask any questions if you have.
Thank you very much, Professor Locke. You have taken us on a tour, fascinating tour of the ocean observations. I was curious to hear more on the impact of climate change, any areas that you have in your research agenda. So if you could tell us a little bit more about the question of sea level rise. Is it really happening? At what speed? This is something that worries us here. And the second question, how much the Maldives can be an experimental laboratory for your, what you call ocean observation?
Yeah.
Thank you.
No, thanks. That's a great question. So sea level rise is definitely something we measure and we see happening on a global scale. I work also in the Arctic Ocean, and I've done some experiments in the Antarctica. And there we can see some real impact. I don't think I'm very old, but in the time that I've been going in the Arctic in the last 15, 20 years, I can see really the difference in how the ice is, and there's much more, there are really large differences. And we're using satellites and using our global network like Argo. We have seen warming of the ocean, so there's thermal expansion, there's real sea level rise happening. But that's like, a lot of the figures that we see usually show kind of that global average. So the same way that there is these different scales, there's a mean circulation. On top of it, there is weather. And I think it's the same is true for ocean, for sea level rise. So each part of the world are kind of like having a different trend in the way that the sea level is rising. And mostly what we're seeing is that there's a little bit more extreme too. So if the ocean is a little bit higher on average, that means that when there's a storm surge, when there is a high tide, then that will really cross a threshold that becomes a problem. So it's not so much the trend that is concerning to us, it's more the fact that the extreme high and the extreme low are gonna be a little bit too extreme for us to cope with. And so a lot of the science that I do is kind of looking at the weather of the ocean. So it sits on top of these large trends, but there are like these more extreme events. And just to address very quickly your question about the Maldives, I think one of the thing that is most fascinating for me about the Maldives is the fact that no matter where you are, you see the ocean. The ocean is around everyone here. And I know for a fact that, the first time I went to sea, there is this feeling that's really hard to express. Like the ocean is such a wonderful and a powerful environment. And I think the ocean is really intrinsically part of what the Maldives is. And you feel that weather, you feel the ocean here in a way that is very unique and very different than what, if I give the same talk in the United States or in Canada, the ocean is kind of a more foreign concept. So I think that's a unique opportunity to understand how that connection between the way we live our lives and the way that the ocean is working is happening. So that's why, in many ways, I'm really excited about being here. And the ocean the Maldives can be really at that forefront of trying to deal with all of this feedback between the policies, the decisions, the way I look at the ocean, and how we deal with it. And I think here you in a sense, you don't have a choice. You live with the ocean.
Thank you for a very informative talk. There are few questions it's related to interconnected only. COVID-19, we have social slowdown all over world, and especially over South Asia. As a scientist, we try to find out what are the changes in the atmosphere. So we found there are lot of changes happened during the COVID, and there is a kind of more sunlight reaches on the Earth. So it's like a 7% we estimated over the South Asia. And at the same times, we have seen that from satellite, there is a change in temperature, sea surface temperature, like 0.5 to 1.5 degrees Celsius. Is it really matching with your observations? And the second questions related to this, you have a long series of observations. Have you seen that definitely you will definitely do this one, but is any idea how far now the satellite measurements and your observations are connected?
Yeah, I think mostly these are great motivation for trying to observe these systems, right? Like the first, if you look back for the exchange and for the circulation that we see here, and what drives really these warm SST that we see in the spring is really that fresh water that comes around. And usually these, to capture this, we saw all of that structure I showed in the glider data. People did 1 or 2 sections, and then they kind of tried to draw the arrows and say, okay, this is how much transport there is at any given time. And the more you look at it, you start seeing a little bit more structure. And then I think it kind of connects a little bit with these questions of sea level rise. Is all the important processes that control this export and control how thin your mixed layer is, which will control how warm it will get because of the heat that you're putting in the ocean, is really kind of that product of that superposition of all of these processes. The coastal trapped waves that are around, the big eddies that are here, the monsoon winds. I haven't. I guess I'm starting I maybe have a 4 or 5 year time series south of Sri Lanka, but mostly the striking part is seeing that variability. So extracting the trend is challenging, but it's a great motivation for me to go back to my sponsors and say, hey, I need to keep doing this for 5 more years. And it's also identifying these questions. What are the metric I need to look at to really kind of be able to know what how impactful it is. So I think that the kind of questions you ask, even though I don't have an answer, for me it's maybe the motivation for collecting more data and also knowing what to look for in the data that you collect. Because we have tons and tons of data, and the challenge is oftentimes to identify the right question that are relevant for all of these scales. So.
I myself was very fascinated by the work you are doing and the information you are getting about the sea surface temperature and the salinity and how it is affecting the Maldives itself, because this is where the currents or the water bodies, the less saline water from the Bay of Bengal and the high saline water from the Arabian Sea are coming and meeting. And that definitely will affect the coral growth, coral recovery, and also the fishery itself. And you have a very nice profile of the thermocline that will also affect the larger tuna species that we have in our EEZ. So I'm just wondering, your device is very expensive. It's about $150,000 US. Yeah. So what type of work we in the Maldives could start to collect data from the oceans with less expensive equipment?
Yes, well, it's always a problem of scale, right? Like you have to, we're all resource limited in many ways. So one of the, with sea surface satellite, you can see right at the top, the very top of the water column, what the temperature is. And this spring in April and May, we saw the sea surface temperature really rising to values that we had never seen before. So every year it seems to be a little bit warmer, and that really this warm temperature really directly impacts fisheries, coral health, and so on. The big question is really trying to get that, what is the structure, the vertical structure of this? And I think gliders are wonderful, but they're also, as you say, they're not, you can't have too many of them, you can't have them. So I think having in the really interesting and key places, having some observations at depth of what's happening. So even having small temperature sensors that you can put in the key coral reefs that you're trying to monitor the health of, and you can relate that data to what's happening on the surface. And the same is true for currents. You can't necessarily go and measure currents everywhere, put these moorings everywhere, but there are probably key areas that are really important for this exchange of water between the lagoons and the interior, that you could have current profilers, ADCPs, moorings. Then you can build this kind of observing system in places that are directly linked to things that you want to understand, and data that can also inform policies or get people excited about the ocean the same way. Like I think, one of the things that is really wonderful, at some point we took a little handheld CTD and we lent it to an organization, the Marine Whale Shark Research Program here, that went around and they had their volunteer take a profile of temperature. And seeing people that don't necessarily have this experience, seeing that the temperature really decreases as function of depth, or that the salinity has some structure, is a great way to communicate that dynamic ocean that we all live in. So I think some real-time data, identifying some key questions, some key places, and drifters and health CTDs, little temperature sensors are not very expensive, and they make some really great projects for students, for outreach, and just explaining that the ocean is this rich environment, the same way that the cloud in the atmosphere is ever changing, the ocean is also ever changing. So that's my...
Thank you very much. We hope to see some wonderful collaborations with you.
I agree, I hope to. But yeah, thank you again for everything.
Thank you. I invite the Vice Chancellor to hand over a token of appreciation for you.
Thank you. Thank you.
Thank you.